Welcome to my next video. Now we're going to discuss answering to CheckCIF alerts to make our CIF file publishable. So first, what does it actually mean? When is a crystal structure publishable? That's something that people ask and discuss a lot, and there are basically only two rules. So firstly, your structure has to be fit for purpose. And the second point is your structure has to be chemically sensible. In general, forget about all the rules that are very stupid, like that your R factor should be lower than 10, blah, 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 because it really depends on the molecule and on your structure. So regarding the first point, crystal structure is publishable when it's fit for purpose. So if you have a structure, such as this one, it's a really bad structure. I can grow it right now. It's a very nice nanoring consisting of 6 porphyrins, and the main reason for publishing this structure was that it's quite surprisingly flexible. Usually we think about pi systems as quite rigid systems, right? But here the nanoring is bent to an elliptical conformation and also co-crystallized with fullerene. So there are one nanoring molecule is surrounded by 6 fullerenes that pi stack to the porphyrin walls. But anyway, the point is, this is not a very good structure. So firstly, you can see that the data resolution had to be cut to 1.33 angstroms because we couldn't really see any diffraction beyond, even when we use synchrotron radiation. You can see that R factors are also not great. We also had to use solvent masking. There is a ton of solvent that is so disordered that there is just diffuse electron density everywhere. You can see that the ellipsoids also don't look great, but the main point, structure has to be fit for purpose. And if our purpose is to show a general connectivity, geometry of the molecule packing without any discussion of bond lengths or angles, then it's totally fine to have a structure like that. But if you wanted to, if you now say in your paper that your carbon-carbon bond is 1.32, then I would say this is not a very publishable structure, because with such bad data quality, you can't really discuss bond lengths. It's essentially meaningless. It also had to be heavily restrained. So again, structure has to be fit for purpose. And the second condition, structure has to be chemically sensible. You cannot publish a structure which contains benzene molecule where refinement indicated bond length of 1.6, or where your benzene is completely boat shaped, right? So your structure has to be chemically sensible, and this structure is both fit for purpose if you are just discussing packing, and it's also chemically sensible, like everything's good. Of course, bond lengths are not ideal, but they are in the range that you can expect from this type of molecule. We didn't discuss bond lengths in the paper. We are just looking at geometry and basically planarity of porphyrins and how these butadiene linkers are arranged in the molecule. You can see that these are kind of in one plane, but these are a bit out of plane, so quite bendy, right? Yeah. So anyway, so let's say we did our final refinement. We are happy with our crappy model, but well, that's as good as we could get with this data. So we want to run CheckCIF, right? So we go to the CheckCIF website, we can upload the file, and usually journals and in general it's a good practice to output response for A and B level arrays. Then we'll copy paste it to our CIF file and we'll be able to answer them. So I already did that, so here is what we get. So we have a couple of alerts. So this alert, whenever you click alert, it will show you explanation. Sometimes this explanation actually makes sense and are understandable, sometimes not really. So we have, for example, this alert. It basically tells us that the resolution is not great, which is, I mean, expected. It's a large molecule, terribly disordered, and well, that's as good as we were able to get it, right? So we will just have to explain that the resolution was limited, right? And like, that's just chemistry. We can't beat the physics, right? High WR2 value, again, just crappy molecule, crappy crystal, we never managed to get anything better. Here, ADPs are a bit wrong. In this case, I think they correspond to the fullerene, which is disorder, but any disorder modeling didn't make much sense, and we just heavily restrained this molecule. The fullerene, low bond precision, again related to crappy data quality and some missing reflections. So these have very low HKL numbers and they are probably hidden behind the beam stop. We have very large cell. There are a lot of reflections, so some of them, the low order one, just overlap with the beam stop, and everything here just basically related to that. So if you go down, you can copy validation reply form, Control C, and put it in your CIF file. So we can go to our CIF file, we can open it. I really don't like this new Windows edit in Notepad. Okay, so we have data, blah blah blah. Here we can change the name that will appear on our CheckCIF report. So for example, I don't know, I love crystals. It sounds like some drug addict said that, but well, let's just leave it like that. Okay, and then we can basically copy and paste that below. So we can put it here and then explain everything, right? So I think it's just important to not have too many letters in one line. So I would say up to this point, if you write, everything will be okay. But if you write a very, very long line up to somewhere there on the right, it might get cut from your CheckCIF PDF and it will not look great. So try to basically don't go further than somewhere there. But yeah, just explain it. And then copy, save, and you can submit it to CheckCIF again and upload a nice PDF. I will show you how it looks like when I did it. So I will close that and open my PDF with responses. So here we can see some stuff. Yeah, again, we use squeeze, so density of the crystal is very much underestimated. But again, if we describe it in a paper, everything's fine. It's just as proof of packing and connectivity and general shape. So we have that lever alert A. As I said, it's related to low resolution. So my response was, the crystals were subjects should be, of numerous data collections, including attempts using synchrotron radiation. The best dataset was selected for structure solution refinement, and although the dataset was measured up to 1.13 angstrom due to lack of reflections beyond that resolution, the data provided a useful model showing flexibility and packing of molecules in the solid state. And I don't think that any reviewer, referee who would read that would, would murder you for not having great data. I mean, that's just understandable. In another structure which was published together with this one, I also wrote that basically these are very huge molecules with size comparable to simple proteins such as insulin. So we are kind of at the border between the worlds of small molecule and protein crystallography in terms of the size regime. So it's perfectly acceptable. Okay. High WR2 value related to pool quality of the crystals, and I also said see the answer to the level A alert, because in the answer to the level A alert I explain why is our data so shitty. So again, related to pool quality of the crystals and disorder, because these are involved in I don't remember whether they are aryl groups or fullerene, but anyway, disorder that couldn't be modeled better. Again, the same thing, and low precision, again related to poor quality of the crystal. C, the answer to level A alert. Also, you can always, with different words, explain the same thing and make the reviewer bored, but I usually don't like that myself, so I just say, well, look at point A. But all of these responses basically are supposed to show someone who reads it that you understand the problem, you know what's going on, you really know what happened to the structure. And here, as I said, reflection is most likely hidden behind the beam stop, and that's it. In this form, we can upload it to Cambridge database and everything's fine. So just to remind everyone, again, firstly, structure has to be fit for purpose, and secondly, it has to be chemically sensible. If your structure has super non-planar benzene or I don't know, some terribly wrong bond lengths or ABTs, just ADPs look weird for no reason. So if you have perfectly good data set with beautiful reflections, the crystal is single, but something's wrong with all of your ADPs, that might mean something else. Maybe your space group is wrong, maybe you have some modulation in the structure, and in these cases that wouldn't be a publishable model. But yeah, so thank you very much for your attention. I hope that was useful, and yeah, I hope you'll enjoy watching other videos. Thank you.